Hi all, I'm here to present our CVPR paper of manipulation localization using a practice scheme. Here's a high-level summary of manipulate MaLP. So we use a template set to perform the encryption onto the real images to make them so that if the generative model tries to manipulate it, then we are able to perform the manipulation localization of where the pixel was actually manipulated. We propose a two-branch architecture with a larger receptive field and a high inference efficiency by using a transformer and shallow CNN network in the training and just using the shallow CNN network in the testing. And we show that our method is much more generalizable across the unseen generative models compared to the passive box. So our contributions include a novel proactive approach for manipulation localization, learning template set unsupervisedly to perform encryption, a plug-and-play discriminator module to improve image generation quality for GMs, and a generalization benchmark consisting of 22 GMs for manipulation localization. So let's come to the passive manipulation localization. So it involves a real image which if a generative model tries to manipulate it to a manipulation image, we basically try to have a manipulation localization module to get the fakeness map out of it. So there are certain weaknesses associated with this kind of passive approaches. Basically, they have poor generalization across unseen generative models. They have low resolution fakeness maps, and they fail on unseen attribute modifications. So instead of just using the images as is for the manipulation localization module, we are proposing a proactive manipulation localization where we first try to add a template to perform image encryption onto the real images and to make the image protected. And this protected image would, if the GAN tried to manipulate it, then we have a much better vagueness map and that is much more generalizable to unseen generative models. Now, there are certain challenges associated with it, basically like formulating the constraints for the template to make because we don't know what is the ground truth of the template. So we have to define some constraints to estimate it in an unsupervised fashion, and we have to estimate a high resolution vagueness map because images these days are in a very high resolution, so we need a very high resolution vagueness map to estimate every pixel, whether every pixel is manipulated or not. And our method should be generalizable to unseen generative models and the attribute manipulation. So keeping these three challenges in mind, we have proposed the following innovations in our work. So we are proposing a proactive scheme, which we train on one generative model and test on 22 generative models. With our scheme is much highly efficient and now can be used as a convenient plug-and-play discriminator. And we also propose an exhaustive evaluation benchmark on GMs for future localization works. So our framework consists of three modules: the encryption module, detection module, and the localization module. The encryption module consists of a template set from which the template is selected randomly to add it onto the images, and a generative model is used in an evaluation mode to perform the encryption. Then we basically have a shared network to and an encoder network to perform the detection, and then a shallow CNN network and a transformer is used in a in a two branch architecture to perform the localization. And these fakeness maps are used as in a classifier Z to perform the detection improve the detection along with the detection module. We have basically certain constraints: the temperature constraint, recovery constraint, localization constraints, and the classifier constraints, which are applied on to improve the performance of the localization module. So coming on to the results, we compare our approach with the passive and the proactive works. Uh, so the passive works basically uh, we have much better localization and the detection, and we and across uh, just one GAN and across unseen GMs and attribute modifications. So the map is able to outperform the prior works for localization and detection, and the map is also does also has better generalization across different facial attributes. Uh, we also show the generalization of map across multiple generative models. So on the x-axis, you can see that we consider three methods: the Resness 50, Chai et al., and Dang et al. Our, our method has much better cosine similarity performance compared to all the three passive works. So proving that the proactive method does indeed has a better generalization performance across these unseen generative models. Here's the visualization for models performance on different data sets, which basically consists of image and which basically consists of faces and non-face data sets or generic image data sets, in which we can see that the fourth row consists of the ground truth fakeness maps, which is the absolute difference between the second and the third row. And we have a many very similar manipulated image fakeness maps for all of these images, telling the effectiveness of our approach across face and non-face datasets. So MAP is able to localize the manipulated regions across different facial attributes and non-face images. We also talk about the MAP using MAP as a discriminator to improve the image generation quality of the generative model. So we basically train we basically fine tune star GAN on star GAN after applying MAP, and the first row basically is the real image. The second is the manipulation done before the fine tuning, and the third is manipulation done after fine tuning. And the scores on top of the images are corresponding cosine similarity, which is we can see that the MAP has better fine tuning the genes with MAP produces better quality generated images. So and it also decreases the FID score. So the indeed MAP is able to improve the generation quality of the images. So in conclusion, the proactive scheme for image manipulation is proposed in the paper, and we basically use a template set using which we estimate this template set using a predefined constraints, and the fakeness map is estimated via two-branch architecture to promote the local and the global level features. We also propose a generalization framework, a generalization benchmark for 22 generative models for future localization works. MAP is able to perform much better than the prior state-of-the-art works, and it can also act as a plug-and-play discriminator module to improve the generation quality of the JTAMs. So thank you for listening. Here's the link to the paper and the GitHub repository. And yeah, please hit me up if you have any other questions. Thank you.